Yes, the test is up till the 23rd, so you have until basically Monday at 11:59 to get it proctored and done. Just remember, you have to have it proctored, so you need to make an appointment somewhere or choose one of your times. If it's me, for instance, that you're wanting to proctor, make sure you let me know. Uh, like today, there was a bunch of times that you could have done it, and I wanted everybody to let me know so I'd make sure I had enough tests online. But I was afraid they might have took that as meaning they weren't allowed to unless they did tell me on time. So I sent out another email this morning slash announcement, and hopefully they know that. But I still have a couple more times listed that I can proctor for you guys. Just look at my announcement in the email because I don't want to try to remember them off the top of my head because I'll make a mistake. Well, last time I gave you an extra credit problem to try to work on. I want you guys to really do that. It's called extra credit six. Let me double check just to make sure. I think I called it extra credit six, and it is. Uh, I think it's said circular motion or something along those lines. I'm looking at the module now, trying to find it. But I do want to make sure everybody does that. It's actually fairly trivial. It's not that hard to do. It's just a little bit of work. But with it, you end up deriving a little bit of confidence of how to work with vectors and vector valued functions, which is really what an electric field is, or a field in physics is really a vector valued function in terms of a vector field. A scalar field is a scalar valued function that is a function usually of three variables, x, y, and z. That's what makes it a field in space. But anyways, let me double check that. Yeah, it's EC space six circular motion. I just altered the instructions on that a little bit based on a student that one of a question that one of my students had. So I've clarified it a little bit. You can actually make, in addition to the table that I put in there, you can make additional columns for the x component of velocity and the y component of velocity, and then for the x component of acceleration and for the y component of acceleration. But you don't really need to do that because if you go through the process, which means you're going to take the derivative of r with respect to t, uh, if you take the time to do that, uh, you'll get the velocity as a function of time. And then I asked you to calculate the magnitude. And if you pay attention and do the magnitude properly and use the trig identity, you'll find that the magnitude of the velocity is a constant. And then you take the derivative of velocity versus time to get the acceleration as a function of time. And again, I asked you to calculate the magnitude of that vector. And again, using a trig identity, you'll see that that too is a constant. Once you have those two constants, it's fairly trivial to graph the velocity and acceleration vectors at each of the 8 points that I gave you. So do that. We're going to jump right into solving our physics problems. And I'm going to start off with an example from the textbook. This is example 5.5, and it says two boxes and a pulley. Figure 5.7a. In figure 5.7a, two boxes are connected by a cord running over a pulley. The coefficient of Great. The yawns are back. The coefficient of kinetic friction between box A and the table is 0.20. We ignore the mass of the cord and the pulley and any friction in the pulley, which means we can assume that the force applied to one end of the cord will have the same magnitude at the other end. We wish to find the acceleration of the system A, which will have the same magnitude for both boxes, assuming the cord doesn't stretch. As box B moves down, box A moves to the right. So that's the actual problem. Let me get it started by drawing a little bit for you guys and sharing my screen. Almost forgot to do that. That would be suboptimal at best. So I'm going to go ahead and share my iPad screen with you guys. Hopefully we're all on the same network, so I don't have to go back and fix that. It looks like we are, so that's golden. Now I've got the chat window off to the side, so I'll remind everybody to go ahead and chat me your first and last name if you haven't done so already. And we're going to get started on this problem five, example 5.5. So example 5, 5. And basically, what we have here is a table with a pulley attached to it. That pulley allows a rope to run horizontally. In other words, it's not lifting up on the box or pulling down on the box. That's why I said horizontally. I'm going to say this object has a mass of 5.00 kilograms. Your book often uses 2 sig figs. I can't stand that. I really like 3 sig figs. So I'm not doing that. I'm doing 3 sig figs. And then over here, we have another box, and this box has a mass of 2.00 kilograms. And we have a massless rope and a massless pulley and a frictionless pulley. Now, if the mass of the if the pulley actually had a mass, then when you pulled from just above the 2 kilogram mass and you pull down on that, then the tension in that part of the rope would have to be a little higher than the tension touching the 5 kilogram, because if the pulley had mass, then the tension would be required to rotate the massive pulley and pull the box. Whereas if you get on the other side of the pulley, in between the pulley and the 5 kilogram mass, and you go to tug it, you'd see that your only job there is to move the 5 kilogram mass. Whereas the other one had the moving the 5 kilogram mass and rotating the massive pulley. But because we don't have that, that means the tensions in the two sides are equal. We do know that the coefficient of kinetic friction between the box and the table is mu sub k equals 0.20. Might as well make that 3 sig figs too, just for the heck of it, though usually 2 sig figs is sufficient for a uh, coefficient of friction. Now, what we're asked to solve for here is the acceleration. I would say an additional thing might be the tension as well, so I'll talk about that too. So when you're doing this type of problem, this is like an Atwood machine, but it's a little bit different in that the two masses aren't both hanging vertically. In this case, I got one mass sitting on a horizontal surface, and the other case is actually hanging. So I need to draw a free body diagram for each of them. And to make things easy, it's really smart for me to use a synchronized coordinate system. And I just made that phraseology up. That's not a real thing or anything. But what I mean by that is if I consider the 2 kilogram mass moving downward as a positive direction, notice that when the 2 kilogram mass moves downward, the 5 kilogram mass has to move to the right. So I will make that a positive direction for the 5 kilogram mass as well. So doing that links those two so that the two accelerations will be exactly the same. If I did something weird, like use a different one, then I'd have to say a sub A is equal to negative A sub B or something like that. So you don't want to get into that world doing that. So let's start off with the free body diagram for the mass sitting on the horizontal surface. So what I'm going to do is I'm going to draw an XY coordinate system. I'm going to treat X to the right as positive because that's going to be consistent with the 2 kilogram mass going downward being positive. So in this case, again, we're treating all objects as if they're point particles. In this case, the object has a mass of 5.00 kilograms, but the object has a normal force acting on it, F sub n. It also has a weight acting on it, and actually, I meant to make that black vector or that red vector green since it's in the positive direction, so I'll draw that back again. So there's my Fn, my normal force. The weight of the box is 5 times 9.8. W equals mg. And of course, 5 times 9.8 is 49 exactly. You'd think I'd remember that, but I didn't. So 49.0 newtons. Now, in addition to that, we're going on the assumption that the box is going to be moving to the right. So I'm going to have a tension acting in the positive x direction. I'm just going to call that T. Again, since the pulley's massless and frictionless, T1 and T2 are the T to the left of the pulley and the T below the pulley are exactly the same. So I don't need to subscript them, but I am going to be sliding this box, so there is actually a friction force F right there. What we do know, of course, is the friction force is kinetic friction, and that's actually equal to mu kinetic times the normal force. So we're going to make use of that. Now, before I do that, I want to go ahead and use my Newton's second law to figure out the actual equations and therefore the normal force and all that good stuff. So the summation of forces in the y direction is equal to mass times acceleration in the y direction. You can see that this box is supposed to be sliding horizontally like that. So the y is, the way I have it drawn, the y is 0 for the box, and it's going to stay 0. Because it's 0 and stays 0, that means the acceleration is equal to 0. And therefore, all I have for this Newton's second law is F normal, which points up, and therefore it's positive, plus, remember, the left-hand side of Newton's second law is always the sum, not the sum or difference. It's the sum. You're always adding them. But adding a negative is the same thing as subtracting, so I usually just write minus there, and that's what I'm going to do now. So I'm going to say Fn minus 49.0 newtons is equal to 0, and that gives me that the normal force is equal to 49.0 newtons, but we should have expected that. Okay, now I'm going to do the summation of forces in the x direction. So the summation of the forces in the x direction equals mass times acceleration in the x direction. This time it's the only acceleration we're dealing with because the acceleration of the 5 kilogram box will be the same as the acceleration of the 2 kilogram box, even though they're in slightly different directions, because we're assuming that the rope isn't going to get slack and the rope's not going to stretch. Therefore, if I pulled the 2 kilogram box down 1 inch, the 5 kilogram box would move to the right 1 inch. If I did it 1 inch in 1 second, the 5 kilogram box would do 1 inch in 1 second. If I did 1 inch in the first second and 2 inches in the second, the 5 kilogram would do the same thing. So I've now shown that not only are the motions the same, the velocities will be the same, and the accelerations will be the same. So now in this case, I'm going to have t, which is pointing in the positive direction, minus the friction force, which is 0.200, times the normal force, which is 49.0 newtons. That's all the forces acting in the x direction, so that's equal to 5.00 kilograms times A, and I'm going to call this equation 1, which is for the normal force. I'm calling this equation 2. I'm going to go ahead and do the computations of this. So 49 times zero point 0.2 gives me 9.8, obviously, because 5 is, zero point 0.2 is 1/5, and 49 is 5 times 9.8. So this will be T minus 9.8 newtons is equal to 5.00 kilograms times A, and that's my equation 2. Now I need to do a free body diagram for the hanging mass. So in this case, I'm going to remember that I used the positive x direction as the direction that the 5 kilogram box was going. So I'm going to say down is the positive x direction. I don't even need a y direction in this case or a y coordinate in this case, but I'll put it there anyway. So we'll say maybe this is y. Doesn't really matter too much. Now in this case, I'm going to say here's my 2.00 kilogram mass. Now, acting on this is the weight of gravity, which is W, and that's, of course, equal to 2 times 9.8, and that's 19.6 newtons. But then I have a tension force T acting in the negative direction. And again, since it's a massless and frictionless pulley, the two tensions are the same. So now I can write the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, I get 19.6 newtons minus T is equal to 2.00 kilograms times A, and that's going to be equation 3. If you look at equation 2 and equation 3, you'll see that the trick I taught you last time with the Atwood, or the time before last with the Atwood machine, works here because 2 has a positive t in it and equation 3 has a negative t in it. So I can just add equations 2 and 3. So add equations 2 and 3. So when I add the two left-hand sides, I get 19.6 newtons minus tension plus tension minus 9.8 newtons. That's the whole sum of the two left sides. Now the two right-hand sides, notice they have a common factor of A. It's 5 kilograms times A plus 2 kilograms times A. So I'm just going to go ahead and call that 7.00 kilograms times A. And now you can see that the T and the T negative T cancel each other out. And I now have exactly one unknown, and that is A. The left-hand side, 19.6 minus 9.8 becomes 9.8 newtons is equal to 7.00 kilograms times A. So we already have the A is, and that should be 9.80, by the way. I didn't write it there, but that is a sig fig we're allowed to have. I just wrote 9.8 for some reason. So now I'm going to take the 9.8 and I'm going to divide that by 7 and that gives me 1.4. So I get 1.40 meters per second every second is the acceleration. Now, that's what we were asked for, but as I told you, we could also go ahead and calculate the tension in the string. That would allow us to find out, for instance, if I wanted to use fishing string, I could say, okay, well, what pound test of switching of fishing string I would need to use to support this mechanism. So this actually allows us to figure out that sort of problem. Now that we have the A, I can just plug the A into either equation 2 or 3. I'm going to apply it into equation or plug it into equation 2 because the T is positive and it's so easy to solve for. So plug, oops, I should probably write that in blue. Plug A equals 1.40 meters per second into uh, 2 gives me T minus 9.80. So remember that is supposed to have a 0 in there. I just put that there now. So T minus 9.80 is equal to 5.00 kilograms times 1.40 meters per second. So 5 times 1.4 obviously gives me 7. So that gives me T minus 9.80 newtons is equal to 7.00 newtons. Therefore, T is going to be equal to 9.8 plus 7. And that, of course, is 16.8 newtons. So not only did I solve for the acceleration, I went ahead and solved for the tension as well. Anybody have any questions on that? So this process with an Atwood type machine is something you guys should be able to do at the drop of a hat. That entails one, Draw a free body diagram for each mass. So you're drawing a free body diagram for the one on the left side of the pulley and the one on the right side or below the pulley, another free body diagram. If it's a two-dimensional motion, like in the horizontal case for the 5 kilogram mass, then you're going to have to do a Newton second law for the Y motion and a Newton second law for the X motion. Write those equations out. If there happens to be a friction, then you're going to need the normal force. But there also might be other reasons you might need a normal force, like they might just ask you for the normal force. But generally speaking, the normal force is absolutely necessary if they're giving you a static or kinetic coefficient of friction, either one, because you need, in order to calculate the friction force, you need the coefficient of friction and the normal force. But then you also need the summation of forces in the y direction, so you do that, and then you write the Newton's second law for the other one. Now, there are Atwood machines that, for instance, have a steep inclined plane on one side and then a different angle, but another inclined plane on the other side, and both of them could have friction, and both of them could have a different amount of friction for each side. So you really got to get used to doing this. I highly recommend you start off with just a plain Atwood machine like we did in chapter 4. Make sure you can solve that even symbolically, just with the symbols like I did for you guys. Do that on your own and then try this one because this is a good second step. And then start trying the more complicated ones. Anybody have any questions on this? I do have the I do have the chat box open, so if you are typing anything, I should be able to see that. And I did ask everyone, I'll remind you again, make sure you chat me your first and last name in case you didn't do so already. Uh, Yep. Actually, they might have asked for the attention. I don't remember saying it in that question, but I just saw that they did solve for it. Uh, where's to find the acceleration? Yeah. Okay. So they just did it extra. That's cool. All right. Now we're going to look at problem 5.6. A skier in figure 5.8 descends a 30-degree slope. If the coefficient of kinetic friction is 0.10, what is her acceleration when she is in contact with the snow? So this is sort of like a problem we've already worked before, uh, but it's a little bit different. So this is example 5-6 or 5.6 is the way I've been calling it. And for that one, basically what we have is an inclined plane, which I'll draw like this. And this angle is theta equals 30.0 degrees. Notice I went ahead and made that 3 sig figs as I likely do. The coefficient of kinetic friction, mu k, is 0.100. As I said, the angle theta was 30.0 degrees, and what they want to know is what is her acceleration. So A is equal to question mark. So in this case, we have an inclined plane and we have a skier on it, and the skier is going down the hill like that, and we want to calculate her acceleration. Now, as I told you, except when we're doing a banked curve, which is part of this chapter, by the way, except in those cases, you almost always want to tilt your coordinate system to be parallel to the incline. And therefore, I'm going to do that here as well. So I'm going to first off draw my inclined plane coordinate system, which should look roughly like this. Okay, and then perpendicular to that, of course, there's my y prime axis, there's my x prime axis. You don't necessarily have to change the names, but I normally like to do that when they're tilted just so you see that it's a little something different. Now, the mass of the skier we don't know, but that shouldn't matter at all. The forces we have acting on the skier are the normal force supplied by the snowy surface. There's Fn right there. We also have the weight, and the weight doesn't actually isn't parallel to either of the axes. So I'm going to draw this vector. Actually, I'll draw this vector as purple, since red and green are the ones I tend to use for positive and negative. Now, this vector is W, which equals M times G. Now, in order to make use of it, we need to take that weight and reduce it to its component vectors, the component that's parallel to the y-axis and the component that's parallel to the to the x-axis. Now, what we want to remind ourselves is that this tilting angle is theta, and therefore, if you look up here, this makes a right triangle. And if this angle is theta equals 30, then this angle has to be 90 minus 30, which is 60 degrees. So that one right there is 60.0 degrees. But what I want is this angle right here. Well, you can see that this line to that line makes a 90-degree angle. So this angle and this angle are also complementary. Since this one's 60, that means this one's going to be the 30. Therefore, I can just go ahead and write theta there as well. Now I can see that the y component of the weight will actually be in the negative direction. And of course, that's given by mg cosine theta. The x component of the weight, however, will be in the positive direction, and that quantity is given by mg sine theta. I can't really, I wrote that theta so small, y'all might not be able to read it, so I'm going to try to make it a little better. So mg sine theta like that. Now I can go ahead and write the summation of the forces. So the summation forces in the y direction equals mass times acceleration y direction. Oh, by the way, I should go ahead and add the friction force. You do definitely want to add the friction force uh, to the free body diagram. So there's my friction force right there, F sub k. And of course, we know F sub k is equal to mu sub k times F normal. It's a lot less complicated than the static friction. So the summation of forces in the y direction equals mass times acceleration in the y direction. As I've argued before, the y acceleration will be zero. If you don't know why, make sure you find out or ask me. Now I have acting in the y direction, I have the normal force Fn, and that's positive, so I wrote it down positive. Then I have minus mg cosine theta. That's the only force acting in the negative y direction, and Fn's the only one acting in the positive y direction, so I have those two are equal to zero, and that tells me that the normal force is actually equal to mg cosine theta. I'm going to call that equation 1 because that's going to come in handy in a second. Now, and notice we don't have the mass, but this is a key thing. When you solve a physics problem and they don't give you a variable, it's perfectly normal for you to go and in fact it's required for you to go ahead and use the symbol for that variable like m that I used here, and just hope that later it's going to cancel out. If it doesn't cancel out, then you have to say, well, I can't solve the physics problem. Okay, or you have to make an approximation of what you think the mass would be, so on and so forth. Now I'm going to do the summation of the forces in the x prime direction. That one was, by the way, the y prime direction. So summation of forces in the x prime direction equals mass times acceleration in the x prime direction. The acceleration in the x prime direction is the one that we're wanting. There's no need to subscript it. In this case, I have mg sine theta is the positive force in the x direction. So I'm going to write mg sine theta. Now, the friction is the negative force, and that's mu times the normal force. So I'm just going to say minus mu k times mg cosine theta is equal to m times a. So luckily we see right here that there's a common factor of m in everything. Notice I did use equation 1 when I put in minus mu k mg cosine theta. That was me making use of equation 1. So it was actually used. Now I'll divide through by m. And when I do that, I get A is equal to G sine theta minus mu K G cosine theta. So I can calculate the acceleration is going to be the sine of 30.0 degrees minus 0.100 times cosine of 30.0 degrees. And then all of that times g, which is 9.80 meters per second every second. So when I go to do this math, it's not terribly hard. I can just take the sine of 30, which you all know is 1/2, and then I can take the point 0.1 times cosine 30, and that gives me 0. It would normally be 0.866 is the cosine of 30, but times point 0.1 makes it 0.86. So I have 0.500 zeros an extra digit that's not a sig fig, and then I have minus the 0.08660, and then all of that times 9.80 meters per second, and zero point 0.5 minus 0.0866 is equal to 0.4134 times 9.80 meters per second. So when I multiply those two, I get 4.051 meters per second is the acceleration. Anybody have any questions on that? And notice I carried it a long way with just the symbols. And because of that, uh, you could see how what the general formula would be for any object sliding down an inclined plane with a kinetic friction mu, a kinetic friction coefficient mu, an angle theta, and it's basically just sine theta minus mu k cosine theta, close parentheses times g. Anybody have any questions on that?
When it comes to the test, if we are like doing the work on this and then we get like a different answer because of rounding,
Mm-hmm.
like as we're calculating it, if we didn't do it like each component by each component and it's slightly different, do
Right.
we still get full credit or like,
Yes, if it's a multiple choice, you choose the best answer. That's always
oh,
the
okay,
result
okay,
with the multiple choice. But if it's not a multiple choice, then you show it to me, and I'll be able to detect whether you rounded it frequently. And sometimes I do take off, like if you round it in one step. Like when I first calculated mg cosine theta, if I rounded that and then I calculated sine theta and then I rounded that and then I took sine theta rounded minus g cosine theta rounded and then multiplied it by 9.8 and then rounded it again, that's the kind of thing that I would possibly take points off for. What you want to do is keep your extra digits for all those intermediate calculations, and then in the end, round it based on where those underlying numbers are. But that being said, very rarely do I take off points for that. I almost never grade on sig figs unless it's specifically a question about sig figs.
okay. All right,
Okay,
thank you.
you're welcome. All right, let's look at a more complicated one. This one's kind of fun. This is example 5.7. In this case, they say a box of mass MA equals 10.0 kilograms rests on a surface inclined at 37 degrees to the horizontal. It is connected by a lightweight cord which passes over a massless and frictionless pulley to a second box MB, which hangs freely as shown in figure 59A. If the coefficient of static friction is mu s equals 0.40, determine what range of values for mass mb will keep the system at rest. And B, if the coefficient of kinetic friction is mu k equals 0.30 and mb is equal to 10.0 kilograms, determine the acceleration of the system. Okay, so again, that's a lot of words. Ideally, you would have the book, at least the e version of the book out so you can look back at it. I'm going to write down the numbers that we had. MA is equal to 10.0 kilograms. Notice I am going to make everything three sig figs. And that 37, by the way, I keep having a random zero show up on my calculator and it always multiplies by zero. So that's a bit of a problem. Uh, let's do 3 divided by 4. I'm going to say this angle is theta equals 36.9 degrees because I recognize they're trying to do a 3-4-5 triangle. Whenever you use a 37 or 51, chances are they're leaning towards a 3-4-5 triangle. So since I want to make this 3 sig figs, I went ahead and just made it 36.9. We have mu static is equal to 0.400. Again, I'm adding an extra sig fig. We have mu kinetic is equal to 0.300. And for part A, we want to know what MB prevents motion. Of course, you could also say what range of what MB causes motion. They're more or less the same, but they are asking what will keep the system at rest. And then part B, they're saying B B is equal to 10.0 kilograms. And what is the acceleration now? Okay, so I'm going to draw the picture real quick just so we have an idea what we're talking about. The picture is essentially this with a pulley attached to the incline. The rope will come parallel to the incline so it doesn't lift up or push down at all. This box has a mass of 10.0 kilograms, and that's the mass we call MA. And then this box over here is the mass we call MB, like that. Okay. So that's our diagram, and this is 36.9 degrees right there. Now, what I want to do is draw a free body diagram for each of these masses because, again, it's like an Atwood machine, so you want to draw a free body diagram for each mass. I'm going to sort of go on the assumption that going up the incline is the positive direction, and I'll stick with that. That means MB going down is positive as well. But to do that, let's go ahead and draw our tilted coordinate system. There's my y prime axis. There's my x prime axis. Whoa. There's my x prime axis. Okay, and I'm going to have a mass of 10.0 kilograms right here. Now, acting on this is the normal force, and also acting on this, of course, is the weight. Again, I haven't, the weight is not parallel to the x prime or y prime axis, so I'm going to use purple. And this would be 98.0 newtons would be that weight. This angle, by the way, is 36.9 degrees. And now, in addition to that, we have a tension that tends to pull this up the incline. So this is the tension here. That's just going to be called T. And again, the pulley's massless and frictionless, and the rope is massless as well. So we can assume the tensions are going to be the same. Not only that, we can also assume the rope will not stretch or get slack. Now, additionally, I'm going to have a friction force that could go either way because that's what I have to do for part A. I have to figure out not only what mass M makes it break and break the friction and causes the box to go up the incline, but I also need to figure out what mass MB causes it to break the friction, the static friction, so that it slides down the incline. So we're going to have in one part, we're going to have friction going down the incline, and then another part, we're going to have friction going up the incline. So I'll write it like this just to say this is the static friction for the different parts. Okay. Now, I do have to break this weight vector up into components parallel to the x and y axes. So the y axis component is going to be negative, of course, and that's 98 times cosine theta, 36.9 degrees. So 98 times 36.9 is equal to 78.36. So I'm saying this is 98.0 newtons times the cosine of 36.9 degrees. And that gives me 78.37 newtons. Notice I carried one extra digit. That's what you're supposed to do. These other digits I didn't carry because I just made them zero. That's why it seems like I didn't. Now, the x component of this weight is also negative in this case. So it's going to be right here. And that one is 98.0 newtons times the sine of 36.9 degrees. And that gives me 98 times the sine 36.9. That gives me 58.84 newtons in that case. Okay. Now I also have a free body diagram for the hanging mass, and that one I'm going to call the x-axis pointing straight down. I'm going to imagine the y-axis is right here, but it's completely irrelevant. This is a mass MB, and in this case, it actually has a weight that is MBG pointing downward, and it also has a tension T pointing upward. So first off, I'm going to try to figure out how big of a mass actually makes the box slide up the incline. So let's solve that. Say what MB is large enough to pull MA up, whoa, up the incline. So the difference here is I have to add a friction force, but now the friction force will be acting in the negative direction. So I'm going to say implies Fk is equal to negative mu k F normal. Okay. We can see from these equations that we're basically going to get Fn. Well, let me write it all in blue. I'm going to get Fn minus 78.37 newtons is equal to 0. So that gives me my normal force. I'm also going to have T minus 58.84 newtons plus or minus static friction is equal to 10.0 times A. And there I just left the uh, unit of kilograms off so I could fit it in that space. So this is the y prime equation. This is the x prime equation right here. And then in this case, for the hanging mass, I've got MBG minus T equals MBA. So I can call this equation 1, I can call this equation 2, and I can call this equation 3. Notice the plus or minus is what's going on here. So right now I'm going to use the minus for this part A that we're working on. So first off, equation 1 gives me that Fn is equal to 78.37 newtons with one extra digit. And then equation 2 gives me that T minus 58.84 newtons. And then I'm going to say minus. Now I'm taking the coefficient of static friction, which is zero point 0.4, and I'm going to multiply it by the 78.37. 0 0.4 times 78.37 gives me 31.48. So I'm going to say minus 31.4, or excuse me, 0.35. Actually, not 48. It's 348. That's why. Okay, everybody see where I got that 31.35? I just, like I said, I'm not writing it out, so I want to make sure everybody knew that came from multiplying the 0.400 times the 78.37 to get the friction force. And that's all of the left-hand side. The right-hand side is then 10.0 kilograms times A. Now, what we want in this case is we want the tension in the string to just be large enough that the acceleration is zero. In other words, we want it to be exactly equal to zero. In other words, we want the tension to be just enough to overcome the 58.84 and the 31.35 newtons. So now all I got to do is use my equation 3 using the appropriate T. So for uh, breakpoint, I'm just going to call this breakpoint because that's really what's happening here. We're getting to the point at which we break the static friction. So for breakpoint, T would equal 58.84 newtons plus 31.35 newtons equals 58.84 plus 31.35 gives me 90.19 newtons. So that's the break point. Now what I want to do is plug that in to equation 3 to figure out exactly what MB would have to be. So to find oops, to find MB. So what we have now is from equation 3, we have MB times G minus 90.19 newtons. And in this case, for breakpoint, we're going to set this equal to 0. And that gives us the ability to find out what MB will be. So MB would equal 90.19 newtons divided by 9.80, oops, divided by 9.80 meters per second per second. And what we get is 9.203 kilograms. So what that means is if MB is 9.203 or larger, then it will slide up the incline. So uh, slides up if MB is greater than 9.203 kilograms. Now I can do the exact same thing, only this time I'm going to count the friction force pointing in the opposite direction. So I'm going to say, what is MB for MA sliding down? So in this case, I'm going to do the same thing I did before. I'm going to take equation 2, only this time I have to use the positive 31.35 for the friction force instead of the negative. So now I'm going to say from equation 2, T minus 58.84 plus, and this is the key part to remember here. Let me go ahead and write that. I'm going to write that in red so you'll see it. Plus 31.35 newtons is equal to, now that would normally be the 10 kilograms times A, but we're again assuming it's zero. And that gives us that T is equal to, notice it'll become 58.84 minus 31.35. So 58.84 minus 31.35 gives me 27.49 newtons. Now I'm going to plug that in to the other equation to find out what the MB would have to be. So again, I'm going to say MB times G minus T equals 0. So let me write it to the next page. So now I have equation 3 gives me MB times G minus the tension, which we just found was 27.49 newtons. And in this case, we want it to be equal to 0 again for break point. And from that, we get that MB would equal 27.49 newtons divided by 9.80 meters per second per second. So 27.49 divided by 9.8 gives me 2.805. And that is kilograms. So what we discovered is this. If the mass is let's say, greater than 28.05 kilograms, but smaller than, and that answer was 9.203, then the boxes will not Move. Oops. Whoa. Keep trying to put an extra hump in my V. All right, so that's one of the answers. Anybody have a question on that? So that's part A. Now part B, they said if the coefficient of kinetic friction is zero point 0.3 and the mass is actually 10 kilograms, what happens? Well, that's easy enough. We're just going to go back and take our equations, and our equations are the following. I have Fn is equal to 78.37 newtons. We also have T minus 58.84, T minus 58.84 newtons. Now, in this case, it's supposed to be plus or minus, but in this case, we're actually exceeding the mass, so we know it's going up the incline, and up the incline is the positive direction. So we're going to put our friction force to be negative, and that's going to be negative mu kinetic because we know it's already exceeded the static friction, so we know it's going to be mu kinetic. And then that part is got to be equal to the 10 kilograms times A. So that's what we need for that part. Then we also have the equation of motion for the hanging mass, and that's equation three. And this one was equation two. Equation three was mBg minus T is equal to mBA. So now I can go ahead and plug in that that is 98.0 newtons. Notice I went ahead and multiplied 10 kilograms times 9.8 minus the T, and that's equal to 10.0 kilograms times the A. So now we can still add the two equations, and this time I'm actually going to add in the FK. But if I add the two equations, the tensions will cancel out, and I'll only have two A's that matter. And actually, it'll become 10 kilograms A plus 10 kilograms A gives me 20 kilograms A. So I now have T. This is, let me state what I'm doing. Adding 2 and 3. So now I'm adding these two. That's going to give me T minus 58.84 newtons minus now the mu k times the normal force has to come into play. So this is 0.300. That was the friction force for mu k times 78.37 newtons. That's our total friction force. And now I have to add to that plus 98.0 newtons minus T is equal to 20. Well, actually, I'll say is equal to 20 kilograms times A. So we can see that the T's cancel one another out. And what we get is instead 98 newtons uh, minus, so 98 minus 58.84 minus zero point 0.3 times 78.37. And that gives me 15. Actually, let me write this back in blue. That gives me 15.65 newtons is equal to 20.0 kilograms times A. So A is going to be 15.65 divided by 20. and that gives me 0.7825 meters per second. That is the acceleration that we should get for part B. Anybody have any questions on that? Now, your book got 2.8 and 9.2. That's exactly, I wrote 28, but it's supposed to be 2.08. Everybody notice it was done right. I just copied it wrong. So I just want to fix that right quick. But yeah, this is all right. It's 2.805. So we got the same results the textbook did. All of a sudden my program's not working properly. And then they said between 2.8 and 9.2, nothing happens. And then they found the acceleration was 0.78. That's exactly the same thing we got, except I carried three sig figs. Anybody have any questions on that? All right, so that's about one of the toughest problems that you would solve this semester until we get to the really complicated algebra that comes with conservation of momentum and stuff like that. But even that, I give you very specific techniques to use, and it won't be so much of a problem. Now, what I want to do is show you how to design a curve. First, we need to work on uniform circular motion. So, what we discovered from our derivation, so uh, from extra credit 6, we know that V is equal to R times omega, and we know that A centripetal is equal to omega squared R. Therefore, we also know that centripetal force or the centripetal acceleration is V squared over R. So that's the major equation that we were going about deriving, and what you were able to do by doing that extra credit is you found the centripetal acceleration is this quantity. Now, this is important. For instance, I normally tell the story about a 60 Minutes episode I watched in the 90s where some people were going around, and they had one guy who was a little bit of a thrill seeker, and he was going around to various outcroppings out in the deserts of Arizona and New Mexico, and he would like set up a swing and then jump off a rock and swing back and forth, under some of these cool structures that you see in places like Utah. And that was pretty fun. But then he decided to go back home and do it from the Golden Gate Bridge. And I don't know if you know this, but the Golden Gate Bridge is such a height above the water that people can actually commit suicide by jumping off of it into the water. The water, you're hitting it so hard that it could literally kill you from just landing in it. And they wanted to do a swing off of it. So, not having much of a knowledge of physics, he weighed himself and all the people that were going to be on it. So they were all wearing like climbing gear, harnesses so that they were safe and would be tethered to a string and didn't have to use their own strength. But he hung six of them from a cable or rope, if you will. And he weighed, of course, the six people, added their weights up, and then said, okay, this came up to 2,700 pounds. And I'm just making these numbers up. This came up to 2,700 pounds. And then he went to like a Home Depot and found a cable that held like 3,200 pounds. He's like, oh, good. It even give me a little bit of margin for error. And everything was great. Well, the problem is he didn't understand physics. So as soon as they jumped off the bridge on the end of this cable, they started to slide down, swing down like this. But in order to maintain a circle, you have to not only hold up the weight, you also have to accelerate it towards the center of the circle at the right rate, V squared over R. And by not taking that into consideration, his cable was way, way, way under or too weak. So the cable ended up breaking. One person hit a boat on the way down. and basically is quadriplegic for the rest of their life. A couple other people's got seriously injured as well, and he got sued, and I think he's maybe still in prison for involuntary manslaughter. So that's the kind of thing that can happen to you if you don't understand physics and you get kind of cocky about stuff. But yeah, in order to maintain a circle, you not only, especially a vertical circle, it's not good enough to just have a string that's enough to hold the weight. That string has got to supply the weight, but it's also got to supply a centripetal force. And force in this case is just mass times the centripetal acceleration. So whatever their mass was times this v squared over r was the additional force that this cable had to sustain, and it couldn't do it. Okay. So with that in mind, let's look at acceleration. I'm going to skip the simple 5/8, which is the acceleration of a revolving ball. No, actually, that one's really too good to skip. So let's do 5/8 real quick. So 5/8 says a 150-gram ball at the end of a string is revolving uniformly on a horizontal circle of radius 0.600 meters, as in figure 510 or 512. The ball makes two revolutions per in a excuse me, two revolutions in a second. What is the centripetal acceleration? So we know the mass m is equal to 0.150. They gave it to us in grams, but I went ahead and converted it to kilograms. Notice it is 3 sig figs, so I'm happy with that. The radius of the circle is 0.600 meters. And we'll also recognize that it says the ball makes 2.00 revolutions in 1 second. So what that means is that basically the frequency, which is revolutions per time, the frequency is 2.00 revolutions per second. Okay. Now, that also means the period, which turns out, we're going to learn this later, but it turns out the period is 1 over the frequency. Think about it this way. If it takes, if it, if 1 second allows us to complete two revolutions, how long does it take to complete a single revolution? Anybody know? It takes 1 second to complete two revolutions. So, how much time does it take to complete one revolution? That's called the period of the circular motion. Anybody have an answer on that? Yes. Yes. Basically, one revolution in half a second. So, yes, the period is 0.500 seconds. Now, what I wrote was T is equal to 1 over F, and that is a fact. It's not just coincidental that it happened this time, it's always true. So we can use that. We want to calculate the centripetal acceleration. That's what the problem is. And we know the formula for centripetal acceleration is v squared over r. We also know that v is equal to distance divided by time, right? That's our original definition. Well, if the thing's going in a circle, then the distance traveled in one period is one circumference. So I'm going to write that as 2 pi times r, and then the period is t, which is the zero point 0.5 seconds. So we can now calculate the velocity as 2 times pi times 0.600 meters divided by 0.500 seconds. So when I do this math, I get 2 times 3.14159 times zero point 0.6. And then I divide that by zero point 0.5, which is the same thing as multiplying by 2. And I get 7.540 meters per second. Notice I'm keeping one extra digit. So now I have the velocity, and all I need for the acceleration is to calculate the v squared over r. So the v squared is going to be 7. Well, let me go ahead and write it this way. Is equal to v squared over r. So this is 7.540 meters per second squared divided by the radius, which is 0.600 meters. Notice squaring the meters per second gives me meters squared per second squared, but then dividing by meters gives me meters per second squared, which is meters per second per second. So I'm going to go ahead and square the velocity. Now I'm going to divide that by zero point 0.6. The square of the velocity was 56.84. And when I divide that by zero point 0.6, I get 94.75 meters per second every second is the centripetal acceleration. And that's what we were asked to find. Anybody have any questions there? All right. The moon's centripetal acceleration, I'll leave for you guys to calculate later, as well as the ultra centrifuge. Now I'm going to work on a car or something other. I'll skip this example 511 as well. I'm going to, you know what? I'm going to have to spend more time on this chapter anyways. So let me go ahead and get you to the point where we're solving for a banked curve. I'll do all this other stuff next time. I think I have chapter 5 due this Sunday. I'm going to have to move it back because I definitely need more time than what we have here. So, banked and unbanked curves, just to get you started on this. I've already given you a little bit of information. I gave you, for instance, the terminal velocity is the coefficient in the formula for the drag, that, F equals B times V. The terminal velocity is mg over b. So we know how to do those terminal velocity problems. Now I need to show you how to tell whether a car has enough friction to make a turn that it's trying to make. So example 514 is what I'm shooting for here. I skipped a lot, but like I said, I'm probably going to spend a little bit more time next time to do some more examples just because we need more and y'all need more experience. But there's a ton of examples on my YouTube channel too. So this is called skidding on a curve. A 1,000 kilogram car rounds a curve on a horizontal flat road of radius 50 meters at a speed of 15 meters per second, which is about 54 kilometers per hour. Will the car follow the curve? Will the car follow the curve or will it skid? Or will it skid? Assume the pavement is dry and the coefficient of static friction is mu s equals 0.60. And B, assume the pavement is icy and the coefficient of static friction is 0.25. Notice they are using the static friction. Like I told you, the very bottom of the tire under normal operations has zero velocity with respect to the road surface. That's why they're in static friction. So what I have here is the mass of the car is equal to 1,000 kilograms. I'm assuming that has 4 sig figs. The radius of the curve, I'm going to make it 3 sig figs. So that's 50.0 meters. The speed, which is v, is going to be, it's going to be 15.0 meters per second. And what we want to know is will it skid or not? So for part A, will it skid if mu static is equal to 0.600? And part B, will it if mu s is equal to 0.250? So that's our problem. Now, what we have here is a road surface. I'm going to represent the car as a dot. I'm going to make this the x-axis, and I'm going to make this the y-axis. It's a horizontal road. That's why I'm not doing any tilting right now. What forces I have acting on it, of course, are the normal force, Fm, And I also have the weight, which is 1,000 times 9.8, which is 9,800 newtons. Uh, I think I can go ahead and write it this way: 980 newtons. And we actually had 4 sig figs, so I'll put it like this. There you go. And now what we're going to have is the car is going to try to make a turn. I'm going to assume the turn is to the right, and therefore the friction force is going to be pushing it to the right. So I'm now going to say that the friction force, oops, that's the wrong color. The friction force F static is that way. Okay. So the summation forces in the y direction equals mass times acceleration in the y direction. This is another case where the y is not going to be changing. So I get that the normal force minus 9,800.0 newtons is equal to 0. So the normal force is 9,800.0 newtons. The summation of the forces, and this is the tricky part here, the summation of forces in the x direction equals mass times acceleration in the x direction. You might be compelled to think that there's no acceleration here, but that's exactly what has to happen. In order for this car to turn, it's got to accelerate to the right. So the forces that I have are just the coefficient of static friction times the normal force, because we're basically saying, hey, I'm going so fast that I might need to use the full strength of the friction force, and the full strength of static friction is mu s times the normal force. So in this case, I'm going to say 0.600 times 9,800.0 newtons. That's the whole friction force right there. That has to be equal to 1,000.0 kilograms times A centripetal. So, what is A centripetal? Well, A centripetal is equal to V squared over R. So, that's 15.0 meters per second squared divided by 50.0 meters. So 15 and 15 is 225. And then I divide 225 by 50, and I get 4.5. So it's 4.500 meters per second per second. I'm going to plug that in there. Now, zero point 0.6 times 9,800 gives me 5,880. So now I have 5,880.0 newtons is equal to 1,000.0 kilograms times 4.500 meters per second, like that. And what we have to figure out is this sufficient? Uh, I just calculated it with the full friction force, but the main thing is I need the right hand side. The right hand side is 1,000 times 4.5, which is obviously 4,500 newtons. And that actually gives us uh, one of those digits is not significant. Now, that happens to be smaller than the actual max friction force. So I want to point that out. This is F static max. Now, what I could have done is just solve for the friction force and saw that it's less than the maximum, and I would reach the conclusion that yes, it can make that curve. So what I'm going to say is the 4,500 is less than F static max implies it can. So that's the answer to part A. Now for part B, the same thing's going on here. We still need the same friction force to be 4,500 newtons to actually make the curve. What we have to figure out now is F kinetic big enough. So is F kinetic large enough? F kinetic is equal to 0.250 times the normal force, which is 9,800.0 newtons. So 9,800 times 0.25 gives me 2450, which is less than 4,500 newtons. So no, you cannot. Okay, so there's the answer to this one. Anybody have any questions on that? All right. So, like I said, that could have been done a different way. Like I said, we might have calculated what force is necessary and then just compared that to the maximum static coefficient of friction. But it's okay. We didn't do that. It's not a big deal. We solved the problem anyways, and we reached the same conclusion they did. In fact, they came up with the conclusion that I did. 4,500 newtons was the force needed, and 5,880 was the max friction, which is what I got, and 2,450 was the max kinetic friction. So, or excuse me, max friction for it wasn't kinetic, it was static. Let me correct that. But that was the max friction for the case of the ice, and clearly the ice was not big enough. So I'll just say F ice. And I don't mean anything by that at all. So, anybody have any questions on this?
So I have like a section that I'm getting a little bit stuck
Hmm.
comprehending. And it's like the in part A, it was asking will it skid at the point 600, and then I see that it was plugged in for the static max portion.
Hmm.
Is that
Yeah, that part is this right here. This is mu static max is equal to 0.600 times 9,800.0 newtons. So that's where that came from, is this quantity right here.
and then okay. Yeah, I might have to just go over that section in the book.
Okay, so what we could have done is we just left it as F, where I wrote F in the F equals MA, uh, the point 0.6 times the 9,800. I could have just left that as F friction because that's what has to make your car turn. On a level road, a horizontal road, if you go to make a turn, the friction force is what's got to push you towards the center of the circle. So I could have just wrote that as friction and then solved it, and I would have found friction force had to be 4,500. Then I'd say, okay, well, is my friction force large enough? Well, the maximum my friction force could be is the mu static times the normal force. And in part A, that was the zero point 0.6 times the 9,800. And that, of course, gave me 5,880, which is quite a bit larger than 4,500. So I knew it was okay and it wouldn't skid. Then in
Yeah.
part B, the only difference was I used 0.25 instead of zero point 0.6.
Okay. Yep. Okay. That makes more sense.
Does that
Thank you.
track better? No problem.
Yes.
Yeah, sorry about the way I did it that time.
No,
I
no, no, no.
don't know what I was
Yeah.
thinking, but yeah, you
No.
guys are free to go. Make sure you chat me your first and last name. I'll wait for the last person to go in case you have any questions. And also make sure y'all get your online test done. Remember, you have to have it proctored. Remember, I've sent you emails on how that can be done. And I'm still working. I have one student who wasn't able to meet any of the hours for the testing center or for any of the hours hours that I offered. So I might be offering one additional Zoom meeting where I can proctor a test for people. As I spelled out in that email, it's got a lot of details you got to read and figure out whether you can do it or not. But make sure y'all get it done. Your test is due by the 23rd, which is Monday at 11:59 p.m. The testing centers do have some testing centers have Saturday hours, and of course they'll all have some Monday hours, but some of them even have nighttime hours. Each campus has at least one night a week that the testing center is open, so you just might have to find what night you're available and then drive to whichever campus has that night available. But let me know if you need any help with anything. I'm here. Have a good one, and we will finish chapter 5 up next time.
Yeah, Professor, this is Benjamin. I just
Yeah.
wanted to make sure that I emailed you saying that I was gonna take my test Sunday, 3 p.m. on a Zoom
Okay.
proctoring thing.
That's cool.
Yeah, I'll just let you know.
No
Okay.
problem. Yeah, the main thing I was asking people to do that just so I could keep track of who's actually scheduling, and then I might be able to send reminder emails to keep people. But yeah, I appreciate it. I just haven't had a chance to reply to that yet. I've been quite busy printing tests and whatnot.
Okay, thank you. Have a
But
good
thanks,
night.
Ben. I did get that. Or
All
Benjamin.
right. Thank
Anybody else have any questions? How about you, Julian? Have any questions? All right. Looks like Julian might not still be here, so I'm going to go ahead and stop sharing. And now I'm going to say bye. Bye, everybody.